Hello everyone and welcome back to the video lecture series for Calculus 1. Today we are going to be starting our first major application of derivatives, which is in related rates. So a related rate occurs in any real-life situation when multiple variables are all changing with respect to a single independent variable. Usually that single independent variable is time, but not always. So for example, when you are blowing air into a balloon, there are a lot of things about that balloon that are all changing at the same time. The radius, the volume, the surface area, the temperature inside the balloon, the pressure inside the balloon, all of those variables are changing, all with respect to the same variable, time. So in related rates, you're going to have multiple variables that are all functions of the same independent variable, usually time. So related rates are going to depend on implicit differentiation. And in related rates problems, we're going to use Leibniz's notation exclusively because it makes it easier to keep track of what is a function of time and what is your independent variable. Now remember, anything that is changing is a function of time and will therefore require either chain rule or some sort of implicit differentiation. So just keep in mind that any quantity that is changing is a function of time and therefore will probably require the chain rule. So related rates can be broken down into four basic steps. So the first step is to identify which rates or variables are known and which you are asked to find. And then you are going to assign variables to those quantities and restate any given rates of change in terms of derivatives. Anything that is changing and you are given a rate of change is a derivative. And please use Leibniz's notation to represent those derivatives so that you can keep track of your variables. Then, step number 3 is to write an equation that relates all of the variables, and you are going to differentiate every single term on both sides with respect to the independent variable. You are going to need implicit differentiation. Any quantity that is changing is a function of time and will require implicit differentiation and probably the chain rule. Then once you have taken the derivative, what you're going to do is you are going to plug in your known data and you are going to solve for the unknown quantity. So we're going to start off with a problem that pretty much every calculus student does, which is called the ladder problem. So let's say that a 5-meter ladder is leaning against a wall, and we're just going to assume that this wall is perpendicular to the floor, and this ladder is 5 meters long. The bottom of the ladder is 1.5 meters away from the wall at time t equals 0 and starts to slide away from the wall at a rate of 0.8 meters per second. What we're going to do is we are going to find the velocity of the top of the ladder at time t equals 1. So for a ladder that is sliding away from the wall, 1 second is actually quite a bit of time. So I'm going to draw our first triangle, which will represent t equals 0. So at t equals 0, that 5-meter ladder is leaning against the wall, and then the base of the ladder, which is right here, starts to slide away. Now, if this is the wall, away from the wall will be a slide this way. So the ladder is sliding this way. And just because I need to assign it a variable, I'm going to assign it the variable x. So x is going to represent the distance between the base of the wall and the foot of the ladder. It starts at 1.5 meters away, and it is sliding away at a rate of 0.8 meters per second. So any rate of change that you are given is a derivative. Now the variable that I have assigned this distance is x, so this distance x is increasing at a rate of 0.8 meters per second. So because the distance x is increasing, that means the derivative of that x distance with respect to time is a constant 0.8. And since the ladder is sliding away, that means this x distance is increasing. So I have left the derivative as a positive 0.8 to indicate that x is increasing as the ladder slides away. Then we're going to find the velocity of the top of the ladder. Velocity is also known as the rate of change of displacement. So it's basically asking how fast is the top of the ladder sliding down. Now I'm going to give that length the variable y, and as the ladder starts to slide away from the wall, the top of the ladder here is going to be moving down. So this y distance, which is the distance between the top of the wall and the floor, I'm representing with the variable y, and as the ladder slides away, y is going to be decreasing. So it is asking us to find how fast is the top of the ladder sliding down. What we are asked to find is the rate of change of y with respect to time. So we are asked to find dy dt. And we're specifically looking at the time t equals 1. Now, after 1 second, a lot of variables have changed here. So in any related rate problem, you have to ask yourself what quantity is changing and, more importantly, what quantities are not. So as the bottom of the ladder starts to slide away, x is changing, so this x distance is changing, therefore it is a function of time. As the ladder slides away, y is also changing, so it too is a function of time. But what about this problem is not changing? This 5. The ladder is a fixed length. It's not one of those sliding ladders. It's just one of those ladders that's the same length all the time. So 5 is a constant. The length of the ladder is not changing. So at t equals 1, we have to keep in mind what variables have changed in that 1 second and which variable has not. The variable that has not changed is the length of the ladder 5. Now, if the ladder started at 1.5 meters away and it is sliding away at 0.8 meters per second, then after 1 second, this x distance is going to be its starting position, 1.5, plus the 0.8 meters, which gives us an x distance of 2.3 meters. Then, of course, the top of the ladder has also slid down in that 1 second. So in that 1 second, the distance y has also changed. How can you use this given information to find y? Well, these are the sides of a right triangle. We have 2 of the sides of a right triangle, and we are asked to find the third. So let's use a little Pythagorean theorem to figure out this distance y between the top of the ladder and the floor. So setting up some Pythagorean theorem, we've got 2.3 squared plus the other leg, y squared, equals the hypotenuse 5 squared. Then, after using a little Pythagorean theorem, you get y is approximately 4.44 meters. Now, of course, as this time goes by, these quantities are going to keep changing, and it is asking us to find the velocity of the top of the ladder at t equals 1. What we have just found here in this 4.44 is the actual y distance. That is not the same as how fast is the y distance changing. So we are asked to find dy dt at t equals 1. So this is where finding an equation that relates all of our variables is going to come in. We have our variables y, x, and let's use this constant 5. What equation can relate the 3 sides of a right triangle? That's the Pythagorean theorem. So the Pythagorean theorem, x squared plus y squared equals 5 squared, is going to be the equation that relates all of our variables. So now that we found the equation that relates all of the variables, we are going to differentiate both sides with respect to our independent variable, time. So I'm going to take the derivative with respect to time of all 3 terms on both sides of this equation. Remember, when your expression is not in terms of the same variable that you're differentiating, you need to use the chain rule. And any quantity that is changing is a function of time and will require the chain rule. So we are taking the derivative of x squared with respect to t. Because the x distance is changing, this requires chain rule. The outside function is the squared, the inside function is x itself. So the derivative of the outside is 2x. Then we're going to multiply it by the derivative of the inside, dx dt. Then, plus, we're going to do the same thing to the next term. We are taking the derivative of y squared with respect to t. Y is changing, therefore it is a function of time, and it requires chain rule. So the outside function is the squared, the inside function is y itself. So the derivative of the outside is 2y, times the derivative of the inside, which is dy dt. Then don't forget there is another side to this equation. The derivative of a constant is 0. So then what we're going to do is we are going to plug in all of our known values and make sure that we actually have all the information that we need, and then we are going to solve for dy dt. So dy dt is what we are trying to find, which means that we will need everything else. So, do we know the x distance at the time in question? Yes, 2.3 meters. Do we know the rate of change of x with respect to time? Yes, 0.8 meters per second. Plus 2 times, do we know the y distance at the time in question? Yes, 4.44. And then times dy dt equals 0. And as gross as this looks, remember, 2 times 2.3 times 0.8 is a constant, so just subtract it from both sides, and then you're going to divide both sides by 2 times 4.44 to get dy dt by itself. So I'm going to leave you guys to do the arithmetic. You should get approximately negative 0.41, and then we're going to talk about units. So first of all, why is the dy dt negative? Remember, y is decreasing as the ladder slides away. So this is velocity. Velocity can be negative when your displacement is negative. So this means that the y distance is decreasing, and is decreasing with units of meters per second. So that is the velocity of the top of the ladder at t equals 1. Now, if you didn't think to do this part here with the right triangle, when you got to this point in your differentiating, you would have realized that you don't have the x and the y distance at the time in question, so you would know that you would need to draw this triangle at t equals 1 to actually find the x and y distance at the time in question. So just remember that when you get to this point after you've taken the derivative, you are only going to have one unknown at a time, which means that you're only going to be solving for one quantity, and that means that you need everything else in the equation. So remember, if at any point you want to try any of these problems before I go over them, feel free to pause the video and then resume when you are done working. So for this next one, let's say that an oil rig springs a leak in calm seas and the oil spreads in a circular patch around the rig. And calm seas means there's no waves or anything because this is calculus 1 and everything is a perfect world because this is only calculus 1. And the oil, forms a perfectly circular patch. So that point right there is the rig. If the radius of the oil patch increases at a rate of 30 meters per hour, how fast is the area of the patch increasing when the radius is 100 meters? So in a case like this, instead of giving us an actual timestamp like the latter problem did, this is just saying that at whatever instant in time when the radius is 100 meters, how fast is the area of the patch increasing? So instead of giving us a timestamp, it's just giving us, okay, at whatever instant in time that the radius is exactly 100 meters, how fast is the area of the patch increasing? So how fast, also known as find the rate of increase of the area of the patch, means that we are asked to find the rate of change of the area with respect to time, or the derivative of area with respect to time. So we are finding dA dt. Now we are given another rate of change. We are told that the radius of the oil patch is increasing at a rate, the word rate indicates, here comes the derivative, of 30 meters per hour. So they just gave us the derivative of r with respect to t. The rate of change of r with respect to time is 30. And I'm going to leave it as a positive 30 because it did specifically say that the radius is increasing. A positive derivative indicates an increasing quantity. So r is going to represent the radius of the oil patch, and a is going to represent the area. So we need an equation that relates a and r. What's the area of a circle? The area of a circle is pi r squared. So this is an equation that relates all of our variables. You have a constant multiple of pi, that's not a big deal, but you have a and r. As long as those two variables are in there with no extra variables, then you're all set. So then we are going to take the derivative with respect to time of both sides. So we're going to take derivative with respect to time of a, then derivative with respect to time of pi times r squared. All right, derivative of area with respect to time. Since a is not being raised to any powers or anything like that, you don't need the chain rule, but you are going to represent this derivative as dA dt. Then this constant multiple of pi doesn't go anywhere, just leave it there. And we're taking the derivative of r squared with respect to t. Remember, any quantity that is changing will need implicit differentiation. Since area A was changing, its derivative was dA dt. As this oil patch grows, the radius is also going to change, so this is going to require chain rule. The derivative of the outside is 2r, times derivative of the inside is dr dt. Because r was changing, it needed a dr dt. It's a function of time. So then, remember, we are supposed to find dA dt, which means that we need to be given everything else. And luckily, dA dt is already by itself. So we have pi times 2 times, do we know the radius of the oil patch at the time in question? Yes, that's that 100 meters. Do we know the rate of change of the radius? Yes, that is that 30 meters per hour. So then dA dt, you can either leave it in terms of pi, which is pretty easy to do, or you can give a decimal approximation, whichever MyMathLab tells you to do. Make sure that you do it, or, whatever. So the big thing here is you need units. So for units, what are the units for area? Well, if all the lengths are in meters, the units for area are going to be meters squared. Per, what were the time units? It appears everything is in hours. And because this derivative is positive, that means the area of the oil patch is increasing at a rate of 6,000 pi meters squared per hour. So in any related rate problem, you should always ask yourself what quantities are changing and what quantities are not, because any quantity that is not changing is a constant and should be treated as such. So let's say that water pours into a fish tank at a rate of 0.3 meters cubed per minute. How fast is the water level rising if the base of the tank is a rectangle with dimensions 2 by 3? So don't make fun of my terrible art. I'm doing my best here. We have a rectangle. That's a rectangle. So this is a rectangular prism. This is not one of those weird fish tanks with like a truncated top or curved sides. This fish tank is a perfect rectangular prism. So water is pouring into the fish tank at a rate of 0.3 meters cubed per minute. Now, if you couldn't figure out what derivative you were just given just by the context of the problem, you can always look at the units, meters cubed. What type of quantities involve cubic meters? That's volume. So they actually just gave us the derivative of volume with respect to time, or the rate of change of volume with respect to time. Now, since water is being poured into this fish tank, the volume of water is increasing, so dV dt is going to be a positive 0.3. So as water gets poured into the fish tank, I'm going to call its water level H. So H is going to stand for the water level. And we are asked, how fast is the water level rising? That is also, in other words, asking us, what is the rate of change of the water level with respect to time? So it is asking us to find dH dt. If the base of the tank is a rectangle of dimensions 2 by 3. So before we even get into the equation that relates all of the variables, you have to ask yourself what quantities are changing and what are not. So as water is being poured in, obviously the volume is changing. So volume is a function of time and it will need implicit differentiation. The water level H is also going to change as water is being poured in. So it too will need implicit differentiation because H is a function of time. However, the base of the tank is a rectangle of dimensions 2 meters by 3 meters. Now, I know that you're all probably thinking, I know what the volume of a box is. The volume of a box is the length times the width times the height. And this will be the volume of the little box of water. However, the base of the tank is going to fill up pretty much instantly. And as water gets poured in, are the dimensions of the base of the tank going to change? No, the dimensions of the base of the tank are not going to change. The only things that are changing here are the volume and the water height. So that base is a constant 2 times 3. So your volume equation, the volume of the box of water, can be simplified down to V equals 6H. Because the base of the tank is not changing as water is being poured in, length times width is a constant 6. So V equals 6 times H is going to be the equation that relates all of your variables with no extra variables. So then I'm just going to take the derivative with respect to my independent variable time of both sides. Now for the derivative of volume with respect to time, because volume is changing, I'm going to represent its derivative as dv dt. And because v was not being raised to any powers or anything like that, I didn't need the chain rule, but I did need to express this as dv dt. Then the constant multiple is 6, you're just going to leave it there. And for the derivative of h with respect to time, because h is changing, it is a function of time. So its derivative is dh dt. So dv dt we were given as 0.3 equals 6 times dh dt is what we are asked to find. So all you have to do is divide both sides by 6, giving you dh dt of 0.05. And the units, what were the units for all of the lengths? All of the lengths appeared to have units that were in meters. Per, the time units did appear to be minutes. So this means that the water level H is increasing at a rate of 0.5 meters per minute. So then for this next one, let's say that you have two small planes that are both approaching the same airport. One is flying due west, this is west, at 120 miles per hour. And the other one is flying due north, this is north, at 150 miles per hour. And we're going to assume that they are flying at the same constant elevation, which means that they form a perfect right triangle in the sky. We don't have to worry about differing altitudes. So if they fly with the same constant elevation, how fast is the distance between the planes changing at the instant when the westbound plane is 180 miles from the airport and the northbound plane is 225 miles from the airport? So again, instead of giving us a timestamp, they are just giving us, okay, at the instant when these two planes are 180 miles and 225 miles away, how fast is the distance between them changing? So you can see from the picture that this is a right triangle. So we're probably going to use Pythagorean theorem again, since we have the three sides of a right triangle. X is the distance between the airport and the westbound plane. Y is the distance between the airport and the northbound plane, and Z is the distance between them. Now remember, the planes are flying toward the airport. So let's just analyze what is changing here and what is not, and more importantly, are these quantities increasing or decreasing? So as this westbound plane flies toward the airport, is the distance X changing? Yes, X is changing. And is X increasing or decreasing? If the plane is flying toward the airport, that means this X is actually going to decrease. So the speed of the plane that we were given, this 120 miles per hour, that is actually a speed. Remember, speed is always positive because speed is just how fast. Speed does not take into account direction, and it does not take into account that the pure derivative of X with respect to time is decreasing. So I'm going to take this 120 miles per hour, which is the speed of the westbound plane, and I am going to adjust it to account for the fact that X is decreasing. So dx dt is actually going to be negative 120 because the X distance is decreasing. Now, as the northbound plane flies toward the airport, is this distance Y increasing or decreasing? It is decreasing. So because it is a function of time, it will require chain rule. And because it is decreasing, this 150 miles per hour is the speed of the northbound plane. So I'm going to change that into a velocity by making it negative to indicate that y is decreasing. So dy dt, the pure derivative, is just negative 150. Then we are asked how fast is the distance between the planes changing. So we are asked to find dz dt, the rate of change of the distance between them, z, with respect to time, at the instant when the westbound plane is 180 miles from the airport, so at the instant when that x distance is 180, and the northbound plane is 225 miles from the airport, so at the instant when the y distance is 225. Okay, so what I'm going to do is I'm going to draw another triangle to represent the distances at the time in question. We don't know the exact time, and it really doesn't matter. We know that at this moment in time, this x distance is 180 and this y distance is 225. Now, as the planes fly toward the airport, is the distance z between them going to change? Yes, z is going to change. So the hypotenuse z, unlike the latter problem, is a function of time and therefore will require the chain rule. So at this instant in time, z has obviously changed a bit. So how do we find the length of the third side if we are given two sides of a right triangle? We can use Pythagorean theorem. So I'm just going to use Pythagorean theorem to find z. So I have 180 squared plus 225 squared equals z squared. So after a little Pythagorean theorem, you should get a z value of approximately 288. So let's find an equation that relates all three of our variables. So the equation that relates these x, y, and z sides in the right triangle is the Pythagorean theorem. X squared plus y squared equals z squared. And unlike the latter problem, all three sides of this right triangle are changing, so they are all going to need the chain rule, and they're all going to have implicit differentiation. So here we go. I'm going to take the derivative with respect to time of all three terms on both sides. Any quantity that is changing will need the chain rule. So derivative of x squared with respect to time, the outside function is the square, the inside function is x. So its derivative is going to be 2x times dx dt. Plus, for derivative of y squared with respect to t, because y is changing, it needs the chain rule. The derivative of the outside is going to be 2y times derivative of the inside, dy dt. Equals, because z is also changing, it needs the chain rule. So the derivative of the outside is going to be 2z times derivative of the inside is going to be dz dt. Now keep in mind, you are only going to be solving for one of these unknowns, and everything else needs to be given to you or easy to find. So dz dt here is what we are asked to find, which means that we need to be given everything else. So let's go through and just make sure that we have everything. So do we know the x distance at the time in question? Yes, it is 180. Do we know the rate of change of x with respect to time? Yes, it is negative 120. Plus 2 times, do we know the y distance at the time in question? Yes, 225. Times, do we know dy dt, the rate of change of y with respect to time? Yes, that is negative 150. Equals 2 times, do we know the z distance at the time in question? Now, if you didn't think to draw the second triangle down here, you would think, oh, yeah, I need the z distance at this time. So at this point, if you didn't do this already, you would need to go find z at the time in question, which we already did. Z was 288. And then that's going to be times dz dt. And as horrid as it looks, remember the entire left side here is all one giant constant. So you just evaluate all of that, and then you're going to divide both sides by 2 times 288 to get dz dt by itself. So dz dt should be approximately or somewhere in the ballpark of negative 192. And then for the units, what are the units for z or all of the lengths? They seem to be in miles. Per, the time units were hours. So because the derivative is negative, that means this is decreasing. So z is decreasing at a rate of 192 miles per hour at the instant when the west and northbound planes are 180 and 225 miles away, respectively. So then for this next one, Let's say that sand is falling from an overhead bin and accumulating in a conical pile with a radius that is always 3 times its height. Conical means it's forming a cone, specifically a circular cone, and looks something like this. The height in this case is not the slant height, it's actually the altitude. So the height in this case is going to be the distance between the top of the cone and the base, which I'm going to represent as h. And r, the radius of the cone, is going to be this variable here. If sand falls from the bin at a rate of 120 feet cubed per minute, how fast is the height of the sand pile changing when the pile is 10 feet high? So again, instead of giving us a timestamp, it is just telling us at the instant when the pile is 10 feet high, how fast is the height of the sand pile changing? So how fast is the height of the sand pile changing? According to the variables that I have assigned, that is actually asking us to find dh dt, the rate of change of the pile's height with respect to time. And the only other quantity that they gave us was sand is falling from the bin at a rate of 120 cubic feet per minute. And if you can't figure out from context what this variable is, just look at the units. What type of quantities have cubic units? That is volume. So they just gave us the derivative of volume with respect to time. And as sand is pouring onto this pile, is the volume of the pile going to be increasing or decreasing? As sand is being poured in, the volume is going to increase, so I'm going to leave dV dt as a positive 120. Now, here's the problem. This is the volume of a cone formula. So the volume of a cone is 1/3 times pi times r squared times h. And if you were to use this equation as is, remember that any quantity that is changing will require the chain rule. So volume, obviously changing, it will need implicit differentiation. As the pile grows in size, the height of the pile is also going to change. And as the pile grows in size, is r going to change? Yes, r is going to change. So here's the thing. The derivative of r squared would be 2r dr dt. We would need dr dt. We would need some sort of information about the rate of change of the radius with respect to time. Anywhere in this problem, were we given anywhere in this problem the rate of change of the radius? No, we were not given a dr dt at any point in this problem. So don't use the volume equation as is. This is an example where we have an equation that does relate our variables v and h, since v and h seem to be the only variables that we're either given information about or that we care about, but it has this extra variable r. So at the moment, we really shouldn't be taking its derivative because the derivative would require dr dt, which we don't have. So the only way out of this problem is to rewrite this equation in terms of the only variables we care about, v and h, which means that we need to rewrite r in terms of the variable h. That is where this part comes in. The radius is always 3 times its height. So I'm just going to translate that sentence into math really quick. The radius is always 3 times its height. So here's what we're going to do. I'm going to take this volume equation, which has too many variables, and I am going to replace this r with 3h. Because r is always equal to 3h, I can replace r in this equation with 3h. Just please use parentheses. So I'm just going to do a little bit of rewriting here. I'm going to replace r with 3h squared times h. And because we are going to have to take derivatives, let's at least simplify this a little bit so that the derivative isn't going to be too bad. So first, when you square a product, you can simply square each part of the product. So 3 squared is 9 times h squared times h. 1/3 times 9 is 3 pi, and then h squared times h, add the powers, you get h cubed. So that is now the new equation that relates just the volume and the height, the only two variables we care about. So now what we're going to do is we are going to take the derivative with respect to time of both sides of this equation. Any quantity that is changing will need implicit differentiation. So is the volume changing? Yes, so its derivative is going to be dv dt. 3 pi is a constant, so you're just going to leave it there, so it's a constant multiple. And for the derivative of h cubed with respect to time, because the height of the sand pile is changing, it is a function of time, and it is going to require the chain rule, where the power 3 is the outside function, and h itself is the inside function. So the derivative of the outside is going to be 3h squared times derivative of the inside, dh dt. So remember, we are asked to find dh dt, which means that we need to be given everything else. So dv dt, they gave us as a positive 120, equals 3 times 3 is 9 pi times, do we know the height at the time in question? Yes, this 10 feet, squared times dh dt. And then all you have to do to get dh dt by itself is divide both sides by 900 pi. I will leave you guys to do that. You should get a dh dt of approximately 0.042. And then for the units, what were the units for all of the heights? It appears that the height was measured in feet. Per, what were the time units? They appear to be minutes. And because this is positive, that means this is increasing, which it should be. H should be positive. So what this means is that the height of the sand pile is increasing at a rate of 0.042 feet per minute at the instant when the sand pile is 10 feet high. So for this next one, we've got another right triangle here, but this one's going to be a little bit different. So let's say that an observer is standing 200 meters from the launch site of a hot air balloon. So in the picture, here's the observer, here's the launch site of the hot air balloon, and this person is standing 200 meters away. The balloon is going to be rising vertically at a constant rate of 4 meters per second. So constant rate, that means we were given one of the derivatives. How fast is the angle of elevation of the balloon increasing 30 seconds after launch? So let's write down what we were given and let's think about what is changing here and what is not. So they already labeled this distance as y. Y is the distance between the ground and the balloon. And the balloon is rising vertically at a rate of 4 meters per second. So that is a derivative. Specifically, the variable that deals with the height of the balloon is y. So they just gave us dy dt. And as the balloon rises, this distance y is going to increase. So dy dt is going to be positive 4. How fast is the angle of elevation, which they gave us as theta, of the balloon increasing? How fast, also known as a derivative, it is asking us to find the rate of change of theta with respect to time, d theta dt. And this time, it actually gave us a timestamp. We're looking at 30 seconds after launch. So let's think about what is changing here and what is not. So as the balloon rises, this distance y is going to change, so it is a function of time. As the balloon rises, the person needs to look higher and higher up at it, so this angle of elevation theta is also changing, so it too is going to need it too is a function of time and is going to need the chain rule. What's the one part of this that is not changing? This 200 meters. At no point did this problem say that the observer ever moved. So because the observer never moved, that 200 meters is a constant. And as we saw, when we have non-changing quantities that are constants, they are really easy to work with in derivatives. So when you are given a constant, use it. It's going to make things a lot easier. So with a balloon that is rising this fast, 30 seconds is a long time. So I'm going to draw another right triangle to represent what this right triangle would look like at 30 seconds. So the balloon up here started at the ground, so it started at 0 and it rose at a rate of 4 meters per second. So this y distance is going to be the rate of change of y, which is how fast it is rising, 4, times how much time has gone by, 30. So if it is rising at 4 meters per second, after 30 seconds, the balloon is now 120 meters high. The observer did not move, so this distance is still 200. And after 30 seconds, this angle of elevation has obviously changed a lot. So we're going to need to find theta at this time in question. We're going to need to find what theta is at 30 seconds. Now remember, I know we could find the hypotenuse, but let's just use what we have. We have the opposite side right now, and we have the adjacent side. Which trig ratio, we're thinking SOHCAHTOA, which trig ratio involves the opposite and the adjacent? That's tangent. So the tangent of this angle theta, we can represent as the ratio of the opposite side, 120, over the adjacent side, 200. So then, we're not going to divide by tangent. What do we do to both sides to get rid of tangent and get theta by itself? We take the tan inverse of both sides. So theta is going to equal the tan inverse of 120 over 200. And because nowhere in this problem did it specify that theta was in degrees, theta is going to be in radians. So theta is going to be 0.5404. Make sure your calculator's in radians. If you did not get this on your calculator, that means you're in degrees. So then, let's go back and let's find an equation that relates all of our variables. We have theta, we have y. Now here's the thing. Whenever you have angles in a right triangle, and we're clearly asked to find d theta dt, so obviously the equation that we come up with needs to involve theta. We are not going to be using the Pythagorean theorem here. Pythagorean theorem only deals with the sides of a right triangle. The Pythagorean theorem has nothing to do with these interior angles here. So if you have a right triangle and you are specifically asked about something with angles, you need to use one of the trig ratios, either sine, cosine, or tangent. But here's the thing. As this balloon rises, is the hypotenuse changing? Yes, as the balloon rises, the hypotenuse of this triangle is going to change. Do we have any information about the rate of change of the hypotenuse? Absolutely not. We have no information at all about the rate of change of the hypotenuse. So, since we really don't have any information on the hypotenuse, don't use a trig ratio that involves the hypotenuse. You will get stuck at the derivative of the hypotenuse with respect to time, and you will get stuck because we don't have that information. So let's use the sides that we do have, the opposite side and the adjacent side. Which trig ratio involves opposite and adjacent? That is tangent. So the equation that relates all of our variables is going to be the tangent of theta is going to equal the opposite side y over the adjacent side 200. And because the adjacent side is a constant, that makes this ratio even easier to work with. And you can always rewrite y over 200 as 1 over 200 times y if that makes things easier. So what I'm going to do is I am going to take the derivative with respect to time of both of sides of this equation, and I'm just going to go ahead and write this as 1 over 200 times y. Remember, any quantity that is changing will need implicit differentiation. So we're taking the derivative of the tangent of theta with respect to time. Because theta is changing, it is a function of time, and therefore we'll need chain rule. The outside function is tangent, the inside function is theta. So the derivative of the outside is secant squared of the inside theta left alone, times the derivative of the inside, which is d theta dt, equals 1 over 200, times we're taking the derivative of y with respect to time. Since y is not being raised to any powers or anything like that, it doesn't need any chain rule, but it does need to be represented as dy dt because y is a function of time. So remember, we are asked to find d theta dt, so this is what we will be getting by itself, which means that we need all other information. So do we know theta at the time in question? Yes. At 30 seconds, theta is 0.5404. So we have secant squared of 0.5404 times d theta dt. And that is going to equal 1 over 200 times, do we know dy dt? Yes, dy dt was 4, so I'm going to plug 4 in for dy dt. And then to get d theta dt by itself, remember, dividing by secant is the same as multiplying by its reciprocal. So yeah, you could divide both sides by secant squared, but before you freak out about the fact that you don't have a secant squared button, remember, dividing by secant is the same as multiplying by its reciprocal. What is the reciprocal of secant? Cosine. So if you just multiply both sides by the cosine of 0.5404 squared, you will get d theta dt of 0.02, and the units are going to be radians per second. Sorry, that is actually going to be a, 0.015. There we go. So that is going to be a 0.015 radians per second. So what that means is that the angle of elevation theta is going to be increasing at a rate of 0.015 radians per second. So then for this last one, let's say that water is pouring into a conical tank, cone, and the tank has a height of 10 meters and a radius of 4 meters, and water is pouring into it at a rate of 6 meters cubed per minute. So this is a rate of change, which means they just gave us a derivative. They just gave us dv dt, and since water is pouring in, the volume is increasing, so dv dt is equal to 6. And this 10 and 4 meters were the dimensions of the tank. So the tank itself is a cone, and the height of the cone, the height of the tank is that 10 meters, and the radius of the tank is this 4 meters. Now, as water is pouring in, the water is going to form a smaller cone of water inside of this larger cone of the tank. So at what rate is the water level rising when the water level is 5 meters high? So inside this tank, we have a cone of water which has a water height h. So h is going to be the water level, and it is the height of the cone of water. At what rate is the water level rising means what we are asked to find dh dt. At the instant when the water level h is 5 meters high. So you might remember from the last problem we did that involved a cone, here is the volume of a cone formula. We have 1/3 pi times r squared h. And you might recognize that we have a little bit of a problem here. R is going to be the radius of the water. At any point, did it tell us what the rate of change of the radius of the water is? It doesn't. And as water pours into this tank, obviously the water level is going to rise, and obviously the volume is going to change. But is the radius of the cone of water going to change as we pour more water in? Yes, as we pour more water into this tank, the radius r of the water is going to be changing. It is going to be increasing. Therefore, r is a function of time, and r will require the chain rule. At some point, we would need a dr dt, which we don't have. So we are not going to be taking any derivatives right now because this would require a dr dt that we don't have. So just like the last time that we ran into this problem, that means that we need to rewrite r in terms of the height h. Now, unlike the last cone problem, we don't have a situation of r is always 3 times the height here. But we do know that this cone of water is contained within a tank of a fixed size. The tank is of height 10 and radius 4. And because this water is inside the tank, these are going to be similar cones. Whenever you have similar figures, that means that the ratio between each of their corresponding sides is going to be proportional. So all of the corresponding sides between the dimensions of the tank and the dimensions of the water are going to be proportional. So I'm actually going to set up a proportion between the height and the radius of the tank and the height and the radius of the water. So I'm going to set up a ratio between the height of the tank and the radius of the tank. And since these are proportional, I'm going to set it equal to the ratio between the height of the water h and the radius of the water r. And remember, the whole goal is to try and rewrite r in terms of h. So I'm going to cross multiply to solve this proportion for r. So I have 10r is equal to 4h. And then I'm going to divide both sides by 10 and then reduce just to make my life easier. R is going to equal 2/5 h. So that means that the radius of this water is always 2/5 times the height of the water. So what I'm going to do is I'm going to come back to this equation here, and I am going to replace r with 2/5 h with parentheses around it. Squared times h. And I'm going to simplify as much as possible to make my derivatives easier. So when you square a product, you simply square each part of that product, and when you square a fraction, you square both the top and the bottom. So 2 squared is going to be 4, over 5 squared is 25, times h squared times h. So then simplifying, 1 times 4 is 4, over 3 times 25 is 75 pi, and then h squared times h, add the powers, we get h cubed. So now that my volume equation is in terms of the only variables I care about, v and h, now I'm going to take the derivative with respect to time of both sides. Remember, any quantity that is changing will require implicit differentiation. So is the volume changing as water is poured in? Yes. So the derivative of volume with respect to time is dv dt. This 4 over 75 pi is a constant multiple, so you're going to leave it there. Then we're taking the derivative of h cubed with respect to time. Is the water level h changing? Yes, so that means it is a function of time and it requires chain rule. So the derivative of the outside is going to be 3h squared times derivative of the inside, dh dt. So we're going to be finding dh dt, which means that we need everything else. So do we know dv dt? Yes, that is equal to 6. Equals 4 over 75 pi is a constant multiple, so is 3. Do we know the water level h at the time in question? Yes, that is equal to 5. And then we're going to multiply it by dh dt. And as gross as this looks, the only thing that you need to do to both sides to get dh dt by itself is divide. So when you divide, you get a dh dt of approximately 0.477. And then for the units for the height appear to be meters. Per, the time unit appeared to be minutes. So in the context of the problem, that means that the water level H is increasing at a rate of 0.477 meters per minute at the instant when the water level is 5 meters high. So that is the general gist of related rates. The key is that you are going to find an equation that relates all of your variables with no extra variables. Any constants, please use, because take advantage of constants, the derivatives are easy. And you are only going to be solving for one unknown quantity, which means that you either need to be given everything else or able to easily find everything else. So thank you all very much for watching. We are going to be doing more applications of derivatives in the next chapter, so stay tuned for that. So thank you all very much for watching, and I will see you in the next video. Bye-bye.